Okay, so I'm going to prove this statement here. It basically is our lemma on our way to proving a bigger theorem called Rolle's theorem. So we got to prove this lemma on the way there. So let's understand what this lemma is saying first of all. So it's basically saying that if we have a continuous and differentiable function on some interval, which means that it's smooth, right, on this interval. So here's some interval a. B is just smooth all throughout that interval. It doesn't instantaneously change its direction, and it's continuous on that interval. If that's the case, and we know that f attains its maximum at C, some point in that interval, and in the open interval, so not at A and not at B, so that means that it attains its maximum at some point over here, C, right? So it'll look something like that, maybe. Okay, where here is the maximum, then we know that the derivative at that point, the slope of the tangent line, will be 0, and that makes sense. This lemma is intuitive, that it actually works out this way, but we have to prove it rigorously. So basically, what we know is that f is differentiable everywhere on this closed interval, which means that the derivative, since c is in that interval, the derivative of this is also in that, the derivative, since c is in this interval, f is differentiable at c. So that means that the derivative f of, what's happening here? What did I do? There we go. Okay, so since it's the case that we know that it's differentiable, it must be that the derivative exists at c. And the definition of a derivative is just this right here. And we basically know that this limit exists. We know this limit exists since it's differentiable. So it's differentiable everywhere on this closed interval, right? This here. So it must be differentiable at C, which is in the open interval. So C has to be somewhere in here, right? And again, we know it's differentiable, so we know that the derivative at C exists. We know this limit exists. Now, with this being said, let's try and understand if we can figure out what this is. We know more information about f of c. F of c is a maximum, okay, which means that f of c is greater than or equal to every other value for x in this interval. So f of c is greater than or equal to f of x for all x in the closed interval a comma b. And basically, this is true for all the x in a comma b. So eventually, right, this h is going to go towards 0, right? This h over here is tending towards 0. So this value for x, right, this is some x value, this c plus h. So as h goes towards 0, this c plus h will eventually be in this interval a comma b, this c plus h. So this would be some x value inside this closed interval, which means that I'd have this relation then, right? It must be that f of c is greater than or equal to f of c plus h. Because again, this c plus h must eventually, as h tends towards 0, be in this interval. It doesn't matter how small that interval is. H is going to go towards 0, infinitely close. So eventually this c plus h value will be in this interval, which will make this inequality true, which will then make this inequality true, that if I minus f of c on both sides, I get this here. When I minus f of c on both sides. And that said a little bit, more cleanly, maybe, I don't know, I like writing it on the left-hand side, that this value, right, is guaranteed to be less than or equal to 0. And that's the top part of this limit. We know that that top part, right, so let's just match this, right? We know that that top part is less than or equal to 0. Now, let's go back and let's understand another theorem that we have, which is difficult to remember, but we want to use it here. We want to remember that if the limit exists, right, then the left-hand limit and the right-hand limit both exist and they equal each other. So then that means that we know that this limit, whatever it is, we know it exists, whatever it is, we know that the limit as h goes to 0 from the left of this limit equals the limit as h goes to 0 but from the other side, from the right. And these two things must be equal, right? If the limit exists, then the left-hand limit equals the right-hand limit. If the left-hand limit equals the right-hand limit, then the limit exists, right? It's if and only if. So that's a statement that we could utilize here, because now we should see that this limit, right, the values here, right, h is going towards 0, but only from the left. So h is strictly negative. H is strictly less than 0 here. So h is strictly less than 0 here. Now this value on the top, right, we said it's still going to be the case that this inequality holds, right, of course, as h goes to 0 from the left. So we know that the value on the top is going to be less than or equal to 0, and then the bottom part is going to be less than 0. So that forces this entire thing, right, this entire limit on the left to be greater than or equal to 0. Because the bottom is negative and the top is negative or 0. So that means that the only options for this left-hand limit is that it's greater than or equal to 0, because the negative divided by a negative makes this positive, and then it could be 0 in the top. It can't be 0 in the bottom, but it could be 0 in the top. So it could be either 0 or greater than 0, this left-hand part. Now, the right-hand part, right, you're going to argue similarly, but we know that this, again, this will still hold, right, this inequality. So I know that the top part is less than 0 or 0. And the bottom part is guaranteed to be greater than 0, which forces this whole limit here to being less than or equal to 0. And we know that these two things must equal each other. Therefore, this forces that the limit is 0, and you've proven the lemma.